Okay, let's unpack this. We hear a lot about the incredible pace of progress in large language models. Bigger models, amazing new capabilities popping up all the time.
Yeah, it's constant. But sometimes it feels like we see the impressive results without really getting why some models seem, well, fundamentally better at generalizing than others, especially on the basics.
Exactly. Like, what is it about the core design, the actual architecture, that influences their most basic abilities?
Right, things like just modeling language itself or, few-shot learning, that bedrock stuff. How does the blueprint affect that?
And that's precisely the question this academic paper you shared tackles head on. Let me get the title right. How does sequence modeling architecture influence base capabilities of pre-trained language models? Researchers from Harbin Institute of Technology and iFlight Tech.
Yeah, Xinlu, Yanyan, Zhao, Siwei, Shijin, Wang, Bingchen, Ting, they're really digging into that core question. How do these different architectural approaches fundamentally change those base capabilities?
It feels like a really crucial academic angle because, the transformer architecture, it's been dominant, right? Self-attention was a game changer.
Absolutely, a massive breakthrough. But we all know the big catch.
The quadratic cost. Especially when sequences get long, it just grinds things down, computationally speaking.
Exactly. And that's why there's been so much work on alternatives, these more efficient stateful sequence modeling architectures.
Right, things like Mamba, RWKV, DeltaNet.
Yeah, gated DeltaNet too. They borrow ideas from linear attention, linear RNNs, and add new twists like data-dependent decay or the delta rule, trying to keep a compact state instead of looking back at everything all the time.
And other research had kind of flagged that these stateful models, while efficient, sometimes struggled with specific, maybe more complex tasks, like retrieval or copying.
Right, associative recall too. Those specialized benchmarks showed some potential weaknesses. But this raises a really interesting academic point that this paper jumps on.
Which is?
Well, the authors ask, okay, are those limitations just for those tricky specialized tasks, or do they point to something more fundamental, a weakness in the model's actual base capabilities? Can they handle basic language understanding as robustly, especially compared to transformers?
And this is where they introduce their first big innovative idea, right? About how we usually evaluate these things.
Exactly. They argue that the standard approach training on these massive, super diverse data sets, what they call mixed domain pre-training, it actually hides the real architectural differences in base capabilities.
How does it hide them?
Well, think about it. If you train on like everything under the sun, then your test data for base capabilities probably looks a lot like some part of that training mix. So the test basically becomes an in-distribution evaluation.
So most architectures will look okay because they've kind of seen something similar before.
Pretty much. The paper shows this in figures 1A and 2A. Under that standard setup, transformers and the stateful models, they look quite similar early on. It just doesn't surface the true underlying generalization power of the architecture itself.
So it doesn't tell you much about how the model would handle language it's genuinely never encountered before, which is key for real-world robustness.
Precisely. So their first big academic contribution here is proposing a new evaluation framework. They call it limited domain pre-training with out-of-distribution ODE testing.
Okay, limited domain pre-training with ODE testing. How does that work differently, and why is it better for spotting these architectural effects?
So instead of the huge diverse data set, they train the models on a much more restricted set of domains, like maybe just the CC and C4 parts of Slim to Chama as an example they use.
Okay, limited input.
Right. And then this is the crucial part. They test the models on domains that were completely absent from that training set. Things like ArcSieve papers, GitHub code, Stack Overflow discussions, stuff the model has zero prior exposure to from its training phase.
I see. You're basically forcing the model to rely purely on its architectural design to figure out this new, unseen data. No hiding behind having seen similar patterns before.
You got it. And they show it works incredibly well for revealing differences. If you look at their figures, 1B and 2B, in this ODE setting, whoa, the performance lines for different architectures just split apart dramatically, and much earlier in training too.
So it clearly isolates the architectural impact on base capabilities.
Yes, it shows that fundamentally architecture matters a lot for how well a model generalizes its basic understanding.
And what was the key finding that emerged from using this framework, especially regarding those stateful models?
Well, it basically confirmed the suspicion. The stateful architectures Mamba, RWKV, DeltaNet, gated DeltaNet, They showed significant degradation in their base capabilities when tested ODE compared to the transformer and transformer plus M.
So the limitations weren't just on those niche tasks.
Nope, this is a really key academic insight from their evaluation method. The problem extends to their fundamental abilities, and it becomes really obvious when they face data distributions they weren't trained on. It's independent of the training data, it's about the architecture itself.
Okay, that's fascinating. So architecture really drives this fundamental generalization, and stateful models seem to have an inherent disadvantage there, at least in this ODE setup, which naturally leads to the next big academic question they tackled. What is it about the architecture that actually determines these base capabilities?
Right, what are the essential ingredients? So they did a bunch of careful experiments, ablation studies, basically taking parts out to see what breaks or what doesn't matter.
And what did they find wasn't the deciding factor for these ODE-based capabilities? Any surprises?
Yeah, some surprises. Things we often associate with these newer efficient models didn't seem to be the key drivers for the base capability part, like Mamba's data-dependent decay, that mechanism for selective forgetting, or its convolution parts. Their analysis, you can see it in Figure 3a and 3b, suggested those primarily impact how fast the model learns during training the conversion speed, but not its fundamental ODE generalization ability. Sometimes taking them out even gave a slight boost to ODE performance.
Wow, okay, that is counterintuitive. What about something like position encoding? That seems pretty fundamental to sequence understanding.
Also interesting, their results in Figure 3c kind of showed that common position encoding schemes, none, absolute, ODERY, even alibi, they mostly yielded similar base capability results, again, affecting conversion speed more than the final ODE outcome. So position encoding in itself didn't seem to be the magic bullet for improving this specific capability either.
Huh. Group norm 2, I think that was in Mama too.
Yeah, Figure 3b again, same story. Didn't seem to enhance base capabilities in their tests. Fell into that non-determinative category.
Okay, so if those aren't the critical factors for ODE-based performance, what did they find matters? What architectural properties are essential?
They zeroed in on 3 key factors. This is really the academic core of their architectural analysis, shown in Figures 3D, E, and F. First one, full sequence visibility.
Meaning the architecture needs to be able to see the whole input.
Essentially, yes. They tested this by limiting the model's architectural view, like using different window sizes, Figure 3D, and they found that allowing the architecture to potentially access the entire input sequence context was crucial. Performance improved significantly with more visibility and degraded when it was reduced. The architecture itself needs the capacity to see everything if necessary.
Makes intuitive sense. You might need info from way back.
Second factor, real relation calculation. This was clever. They were inspired by older work showing that, in that standard mixed domain training, you could replace the transformer's query key calculation with just random numbers and it didn't hurt that much.
Right.
But they hypothesized, maybe for base capabilities, especially ODE, that real calculation does matter, and bingo. Their tests, Figure 3e, showed models whose architecture couldn't compute actual data-driven relationships between sequence parts suffered a big performance hit ODE.
So it's not just seeing everything, but the architecture needs the machinery to figure out how different parts genuinely relate.
Exactly. And the third piece is non-uniform distribution. The idea here is simple. An architecture that just averages everything it sees is probably not going to be very good.
Right, it needs to focus.
Precisely. They tested this by tweaking the architecture's ability to focus using something like softmax temperature to control how peaky the attention distribution could be. And Figure 3F shows that as the architecture gained the ability to create a more non-uniform distribution to strongly focus on specific relevant bits based on those calculated relationships, base capabilities got better.
Okay, so let me recap those 3. The architecture needs 1, visibility over the full sequence, 2, the ability to calculate real relationships, and 3, the capacity to focus non-uniformly based on those relationships.
You nailed it. And putting those 3 necessary conditions together, full sequence visibility, real relationship calculation, non-uniform distribution, leads directly to their central innovative idea, the core design principle they propose.
Which is?
A sequence modeling architecture need possess full sequence arbitrary selection capability to avoid degradation in base capabilities.
Okay, full sequence arbitrary selection capability. That sounds important. Break that down. What does it mean for an architecture to have that?
It means the architecture isn't fundamentally limited by only looking at a compressed state or a fixed local window. It has to have the built-in capacity to reach back across the entire sequence history and selectively pick out any piece of information based on calculated relevance to the current step.
So architectural freedom to grab relevant info from anywhere, not just nearby or summarized?
Exactly. It's about the mechanism having that potential reach and selectivity. And they emphasize this as an architecture design principle. It's about the underlying blueprint, not just whether the final model happens to be good at a retrieval task, although models built this way tend to be.
Okay, a fundamental property.
Yes, and to really prove this principle academically, they did something else really innovative. They designed brand new, super simple architectures whose whole purpose was just to embody this full sequence arbitrary selection idea. Then they tested those using their OBI framework.
Oh, that's cool. Building minimalist models just to test the principle. Tell me about them.
The first one is called the top one element selection architecture. It's described as extremely minimalist. Seriously simple. You can see the diagram in figure 5a. Its whole logic is calculate relevant scores across the entire sequence, find the single element with the highest score, and just use that one.
Wow, okay, that's way simpler than a standard transformer layer summing up weighted info from everywhere.
Massively simpler, but it directly implements that core principle. Arbitrarily select from the full sequence based on relevance. And the validation was pretty striking. Figure 6a and 6b showed its OD-based capability performance was almost on par with Transformer++ at both 110M and 1.3b parameters.
So it didn't show that degradation the stateful models did good.
Exactly. It held up. Table 2 shows it's decent in few-shot learning too, comparable to Transformers, and Table 1 shows it smashed the stateful models on retrieval tasks. So this super simple design really supports their principle.
That's powerful evidence. Did they build anything more complex based on this?
Yes, they introduced the top one chunk selection architecture. This one is framed as a more practical generalization. The idea, shown in figure 5b, is similar, but instead of picking just one element, the architecture selects the single most relevant chunk of keys and values from the whole sequence.
Ah, like a whole continuous block.
Yeah, based on calculated relevance. And then it performs a more standard attention-like calculation, but only within that selected chunk. So it still has the arbitrary selection from a whole sequence, but computation is focused, making it potentially more efficient.
So it dynamically finds the most important historical window, basically.
That's a good way to put it. And they made two versions. Top one chunk, exact, using the full probability calculation to pick the chunk, and top one chunk approximate, which simplifies that selection calculation for speed, kind of approximating relevance based on the query and the chunk's average key value.
And aiming for practicality means they also looked at speed, right?
Absolutely. A key practical innovation here was that they actually designed and implemented custom GPU kernels for this top one chunk selection approach. You can see an illustration in figure 5b. Making it run fast was a big part of demonstrating its viability.
Okay, so how did these chunk selection models perform? Did they validate the principle and offer practical benefits?
Yes, quite well on both fronts. Their ODE-based capabilities, again, were close to Transformer++ and much better than the stateful models, figure 6a, 6b, and figure 7 for long sequences. They also showed strong few-shot learning, table 2, and really good retrieval, especially beating stateful models significantly on long sequence retrieval tasks, table 1, table 3.
And the efficiency part. How did the speed compare?
Table 3 shows they achieved competitive speeds, especially the approximate version, which was reportedly comparable in speed to Mamba 2, which is a very fast stateful model.
So potentially getting transformer-like base capabilities with Mamba-like speed.
That seems to be the promise. They also mentioned fairly that other groups independently came up with similar approximate selection ideas around the same time, like DeepSeek, NSA, KimiMoba. But they highlight their unique contributions. The foundational top one element model, the top one chunk exact variant, the whole theoretical underpinning with the principle, and the specific GPU kernels they developed.
Gotcha. So these new architectures are both academic validation and potentially practical paths forward. Did the paper mention any limitations to their findings?
Yes, the main one they point out is that their conclusions are based on models pre-trained using the standard language modeling objective. So they caution that the findings might not automatically apply if you're using different pre-training methods.
That's a reasonable caveat. Always more research to be done.
Definitely.
Okay, so wrapping this deep dive up, this research really seems to clarify something fundamental. It strongly suggests that the architecture itself has a profound impact on an LLM's base capabilities, especially that crucial ability to generalize to unseen data.
And it makes a strong case that our standard train-on-everything evaluation methods were actually masking this architectural effect. Their proposed O framework really brings the differences into sharp relief, particularly highlighting potential weaknesses in stateful models regarding these core abilities.
And the central academic contribution feels like identifying and then validating this full sequence arbitrary selection principle. That idea that the architecture needs the freedom to reach anywhere in the history based on relevance seems key for robust base performance.
Exactly. And those novel, simple architectures, top one element, top one chunk, they're not just cool experiments. They provide really elegant validation for the principle. and show concrete ways you could build models that potentially offer both strong generalization and efficiency.
For you listening, this isn't just some abstract academic exercise. Understanding these kinds of principles, what makes an architecture fundamentally robust, is critical if you want to grasp how the next generation of AI models might be designed. We're talking about models that aren't just bigger, but better able to handle novelty.
It really shifts the design focus, doesn't it? From just optimizing existing structures to thinking about what architectural properties are truly necessary for the capabilities we want.
So, thinking about this full sequence arbitrary selection principle, what does its importance suggest for where efficient sequence models might go next? Does it mean we'll see a comeback of more attention-like mechanisms, maybe clever new variations? Or could we find ways to give stateful models this kind of arbitrary selection power? What questions does this raise for you about how these incredibly complex systems are built and how they learn to understand our world?